Welcome, everyone. For today's prep, we're going to be introducing the idea of spherical coordinates, and we're going to see how we can use this to help with triple integrals, or certain types of triple integrals. So first, what is the spherical coordinate system? And this is a way to, kind of another way to represent a point sitting in three-dimensional space. So we're going to have some equations that we can use to kind of convert back and forth. But first, let's kind of look at what this coordinate system does. So let's look at this little graph here. We have a point sitting in three-dimensional space, and we've graphed it in the regular XYZ coordinate system here. So here's our point. Here's our point P that we're interested in. And normally, we describe this with three coordinates, X, Y, and Z, regular rectangular coordinates. What we're going to be doing now, though, is we're going to be describing this in spherical coordinates. And what we're going to be using are three different values: rho, theta, and phi. All right, so what do these represent? Well, let's start with the first one, rho. So Greek letter rho kind of looks like a fancy little P there. And this represents the distance between our point and the origin. So distance between origin and P. So we have our origin where it usually is, we have our point P, and rho is the length of that line segment connecting the origin on our point P. And we're primarily going to be using rho values that are greater than or equal to 0. All right, so that's the first one. So distance away from the origin. Now, what about the next value? This is theta. And this is going to be an angle. And what this angle measures is very similar to the angle measurement used in cylindrical coordinates and polar coordinates. So if we have our point P, if we project that down onto the XY plane and look at the kind of the projection, theta measures the angle in between that ray. So we have this ray sitting on the XY plane, and then we have our positive x-axis, and theta is that angle there. So the value for theta is same as cylindrical, what we did in cylindrical coordinates. All right, so what about the new one? Phi, or phi. What does this represent? So again, theta represents the angle in between this ray and the positive x-axis. Phi is going to be the angle between this ray connecting our point and the origin and the positive z-axis. So phi is going to be the angle between the ray connecting the origin and the point P and the positive z-axis. All right, so let's look at where that is. So here's our positive z-axis, and then the ray connecting points starting at the origin and going through our point P, and phi is going to be this angle here. So we have the angle that we need to go. So these two angles kind of give us the direction, and then rho is telling us how far we go in that direction. All right, so what are the equations that we can use to convert back and forth? Well, x is equal to rho times sine of phi times cosine theta. Y is equal to rho times sine of phi times sine of theta. And then z is equal to rho times cosine of phi. And, well, rho is our usual kind of distance here. So in this case, it's just the equation of a sphere. Rho squared is equal to x squared plus y squared plus z squared. And that's kind of why it's called spherical coordinates. All right, when we look at this, it looks like a lot to remember, but there is some kind of overlap here between the other coordinate systems that we've seen. So we want to think of rho as kind of like the radius. It really is. It's the distance from to the origin. And so we have the radius times cosine theta. This is kind of our standard polar coordinates. The only thing new there is now we have the sine of phi thrown in. Same thing for y. If we look at the equation for y, part of it is very similar to what we've done in the past. Rho times sine of theta. Same as polar coordinates. Now the part that's new is now we have the sine of phi thrown in there. So the x coordinate and the y coordinate, they kind of have that polar coordinate look to them with this extra trig term in the middle. And then z is, completely new. All right, so really the way to get a handle on this new coordinate system comes from thinking about what this angle phi is. And again, it's the angle in between this ray and the positive x or positive z axis. So we're going to be looking at values for phi. I'm going to keep alternating back and forth, phi or phi. You'll hear it pronounced both ways. I think the correct pronunciation is phi, but phi is also fairly common. So we're looking at this angle phi, and the smallest this angle can be is 0. That's what we're going to be considering, the smallest value there. And that is, if this angle is 0, that means we're on the positive z-axis. Okay. And then the biggest this value can be is pi. So if we go halfway around the circle, that's going to take us down to the negative z-axis. And that's as far as we're going to go. So that's going to take us to the negative z-axis. And then right there in the middle, but halfway between 0 and pi over 2, that would actually give us all the points on the xy plane. All right, so let's try an example here. Let's look at example 1. We have this point 2, comma pi over 4, comma pi over 3, and we want to convert this. It's given in spherical. We want to convert it to regular rectangular coordinates. So when we're given a spherical coordinate for a point, the first value here is rho. So when we look at this, the rho value is 2. The theta value is pi over 4, so that's the next one. And then our phi value is pi over 3. And so these are our spherical coordinates, and we want to figure out what is x, what is y, and what is z. So we take these three values, and we just plug them into those x, y, and z equations. Not too bad. So it's not too bad to go from spherical to rectangular. We just kind of plug in. All right, so what is x? X is rho times sine of phi times cosine of theta. What was y? Y is rho sine theta, so our usual polar coordinates, but then we throw sine of phi there in the middle. And then z is rho cosine phi. All right, so now we just plug in. So plug rho into each of these, and then whenever I see a theta, I'll plug in pi over 4, and then whenever I see a phi, we're going to do a pi over 3. So when we plug these in, what do we get? 2 times sine of pi over 3 times cosine of pi over 4 for x. And that actually simplifies. So sine of pi over 3 is square root 3 over 2. And then cosine of pi over 4 is square root 2 over 2. And this ends up simplifying to square root 6 over 2. So that's our x-coordinate. Play the same game for our y-coordinate. So plugging in, we get 2 sine of pi over 3 sine of pi over 4. And cosine of pi over 4 and sine of pi over 4 are actually the same value. So we end up with the exact same value here for y. Kind of a nice coincidence. Usually doesn't happen. And then what about z? Well, again, rho is 2. And then we're doing cosine of phi, which is pi over, not pi over 4, pi over 3. And cosine of pi over 3 is 1/2. So we end up with 2 times 1/2, which is equal to 1. So when we write our rectangular coordinates, the point was given 2 comma pi over 4 comma pi over 3. This is spherical. And what we did is we converted that into rectangular coordinates, our regular Cartesian, square root 6 over 2 comma square root 6 over 2 comma 1. And so we can plot that point in our regular XYZ space. And again, we want to think of rho and phi here as telling us kind of giving us information about the direction. So theta tells us kind of which direction to turn, and then phi is telling us kind of how much to lean, and then rho is telling us how far to go in that direction. So theta here was this angle, phi, that angle there, and then rho tells us how far to go off in that direction. So the two angles give us a ray, and then rho tells us how far to go. And that's kind of helpful. You want to think of theta as just like you're in a chair and you're turning. That's what theta is. It's just telling you, all right, which direction am I going to look at? And then phi is telling you, all right, which way am I going to tilt my head? And then rho is telling you, all right, now that I found my direction, where I'm looking, how far do I actually go off in that direction? This is kind of how you want to think of these spherical coordinates. All right, what about the next one? We have this point 0, comma 2 square root 3, comma negative 2. Now this one's given in Cartesian coordinates, and we want to find the spherical coordinates for this point. So kind of going back takes a little bit more work because we actually have to figure out, we have to, kind of solve some trigonometric equations, which, not too bad, but it takes a little bit more work. So let's start with the easy one. So to get this into spherical coordinates, we need three things. We need rho, we need theta, and actually we'll do that one last. We'll do phi, and then we'll do theta last here. I guess there's probably not too much of a reason, but, well, I think this is a good order. And the reason why is because rho, we have a nice equation that tells us how to immediately get it. So rho squared is equal to x squared plus y squared plus z squared. We know what all of these are, so we can immediately just solve for rho. So if we plug in, x squared is 0 squared. Y is 2 square root 3, so we're going to square that. And then z is negative 2. So if we calculate this is going to be 12. This is going to be 4, so we end up with 16. And that tells us then if we do the square root, rho is going to be, well, plus or minus 4, but we want to use positive value. We don't want to overcomplicate things, so let's use the positive value there. Now, once we know rho, once we know rho, then we can use our z equation. So z is equal to rho times cosine of phi, we can use this z equation then. We know what z is, we know what rho is, and we can use that to solve for phi. All right, so let's plug in our values. We know z is -2. We know rho is 4. And we don't know what cosine of phi is. So we'll just leave that as is. If we solve this equation now for the unknown trig term, we end up with cosine of phi is equal to -1/2. So divide both sides by 4. And there is... well, let's think. There is... We think about what cosine looks like. Cosine has this look to it where it goes between 0 and 2 pi. And actually, let's draw this one out. So cosine has this look to it where it does one full revolution between 0 and 2 pi. And we only want phi values that are between 0 and pi. So we're only looking halfway, up to the halfway point of cosine. And there's only one spot where cosine is equal to -1/2. So we can actually use our inverse trig function, our cosine, if we don't remember, to figure out what this is. But it turns out that this is phi equal to 2 pi over 3. So another way to remember that is... Yeah, let's spend a little time. It's not going to hurt. So let's spend a little time reviewing some little trick here to help remember. So here's our XY plane. And we can use the unit circle to help us remember different trig values. So when we plot a point, again, let's look at the unit circle. And kind of the main angles that we consider are theta equals 0, theta equals pi over 6, theta equals pi over 4, theta equals pi over 3, and then we have the y-axis there, which is theta equal to pi over 2. All right, and we can remember our cosine. So these are kind of the main angles. We have 0, pi over 6, pi over 4, pi over 3, and pi over 2. And these are the ones we use most often. So if you're going to be solving trig functions, these trig equations, these are the ones that are going to show up probably the most often here. And a way to remember the values is if we think of a point sitting on our unit circle, the x-coordinate is cosine, and the y value is sine. And so the way to kind of think of this, there's a kind of a little trick to write it out. Cosine of theta, well, let's look at this point here. And we can write this as kind of a little bit more. We're going to write this as square root 4 over 2, comma, square root 0 over 2. And, excuse me. So this is just 1, and that's the cosine value. So cosine of 0 is 1. This is just 0. Sine of 0 is 0. All right, so we're not going to use it to help us remember this point, but we are going to use it to help us remember the values at these other points. And so what happens is as we go counterclockwise around this section of the circle, we kind of either, the term under the square root either counts down or counts up. So we go down to square root 3 over 2, and then the y-coordinate's going to be counting up. So we go to square root 1 over 2. Then for pi over 4, we count down in the first coordinate, so square root 2 over 2, and then we count up in the second coordinate, square root 2 over 2. And then for our pi over 3, again, the first coordinate we count down, so we get square root 1 over 2. And then in the third coordinate, we count up, so we get square root 3 over 2. And then for the last one, pi over 2, and we probably don't need to have this one remembered this way, but the pattern kind of continues. This one is square root 0 over 2, comma, square root 4 over 2. And so if we want to remember what is cosine of what is cosine of pi over 3, well, I can just look at the x-coordinate then, and it's square root 1 over 2, just 1/2. If I wanted to know what is sine of pi over 3, well, then I can just look at the y-coordinate there, and that tells me my sine value. So if you have a tough time remembering these different kind of trig values, doesn't hurt to kind of use this to help you remember. Now in this case, and the nice thing is, once you know these angles, then you can use symmetry to figure out the value of the angles in the other 3 quadrants. So cosine of phi equal to negative 1/2. Well, we want some value over in between 0 and pi. So theta equals pi is the negative x-axis. And we look for where cosine is equal to 1/2. We see it right there. Cosine is equal to 1/2 in our first quadrant. And then we just look at the mirror image of that over into the second quadrant. And in this case, this would be theta equal to 2 pi over 3. But now our cosine value, it was positive in the first quadrant, but now over here, the cosine value, the x value, is going to be negative. So it would be negative 1/2. So this is kind of helping us locate where cosine is equal to negative 1/2. Of course, you could just use the inverse trig function as well. All right, so now we just need to get theta. So let's get our theta here. And now once we know these two values, then we can use one of the other equations to figure out theta. So let's use our x. So we can use our x equation, plug in what we do know. So we know the x value is, what was the x value? The x value was 0. Our rho value was 4. And then we know phi is 2 pi over 3, so we're going to have sine of 2 pi over 3. And the thing we don't know is cosine theta. All right. So, well, let's actually put this unit circle to work. Sine of 2 pi over 3, what would that be? So we look. We find pi over 3 in the first quadrant. Now we want to know sine. So sine is the y value. So square root 3 over 2. But now we're not talking about pi over 3. We're talking about 2 pi over 3. So we look at the mirror image over in the second quadrant, and we see that the y values are the same between those two. We have this point here and this point here. The y values are the same. So sine of 2 pi over 3 and sine of pi over 3 are going to have that same value. So we end up with 0. 0 is equal to 4 times square root 3 over 2. And then we don't know what cosine is, cosine theta. So if we simplify this, well, we could divide by all of this, and we get cosine equal to 0. And cosine of 0, that happens at pi over 2. Again, if you don't remember cosine of 0, cosine is the x quadrant or x value. So we just look. Main angle is square root 4 on top, then square root 3, square root 2, square root 1, and then we get to square root 0. So at pi over 2, that's when cosine is equal to 0. All right, so, again, you could just use trig, the inverse cosine function as well, but, just a little trick, so maybe you can just kind of start memorizing these as well. All right, so now we just put it all together. And so what we found is that in spherical coordinates, our point was 4, comma, what did we find? We found pi over 2 for theta. Left right away. So we found 4 pi over 2 and then 2 pi over 3 for our phi. And we put them in that order. So rho, theta, and phi. All right, so hopefully a little bit more practice using these trig functions. And what we're going to see is how we can actually use these to help us with certain trig integrals. And the kind of key here is going to be whenever we start talking about spheres, whenever we start seeing a lot of x squared plus y squared and plus z squared getting thrown around, we're probably going to want to convert our triple integral into spherical coordinates. So we'll see that next time. Bye-bye.